Colin OFlynn, and I'm presenting the session to you, BAM the BAM, Electromagnetic Fault Injection in Automotive Systems. So in this talk, I'm going to talk a little bit about some work I did looking at a engine ECU from a fairly recent, at the time anyway, vehicle, and how we can use electromagnetic fault injection to gain access to it. But more generally, I'm not going to concentrate just on that specific device, but on how these types of attacks are relevant to automotive and embedded systems in general. So I'm coming to you from Halifax on the east coast of Canada, somewhere over here. I'm not, unfortunately, meeting with everyone in person like we would normally get the chance to do. So some people might say, like, where is that? There's not as much around tech-wise, but it's been not a terrible place to spend the last year and a bit. That has been a lot of time without travel. Professionally, though, I'm normally known for a tool called Chip Whisper, which I've presented originally at Black App, and then also some work I've done with it. Part of it is this open source hardware capture and fault injection tooling. Since then, there's all sorts of tools that have developed around it. So I'm going to be using something called Chip Sharder I developed as well. Parts of the tooling are open source, parts of it are not. So depending on where we get into, there's some various, legal for Chip Sharder. I'll be talking about this high voltage tool that required us to get safety testing. So there's a lot of pretty interesting, not just technical side to this that is a topic for another presentation. But I also work on a lot of educational resources. So there's a lot of tutorials I'm going to link to that are just freely available, talking about fault injection, power analysis, things like that. More recently, too, actually, for the past few years, I've been in release with a book with a colleague, Jasper, who works at a company, Riscure, who also does various tooling at an even sort of a really high level of engagement. And so there's this book that should be available that will actually cover some of this electromagnetic fault injection work I'm talking about. So if you're curious, that's another great resource I'm going to plug, of course, now. But what got me interested in this? Basically, I was, someone had sent me this article. This was a while back. So this project really did start in sort of 2019. And it was that GM had this ECU that was unhackable, right? Which is, of course, like a risky thing to put out there. At the time, I found one of the ECUs, this E99 ECU, and it was actually tuned. So the interesting thing I want to mention is that, there's a lot of interest for unlocking these from a tuner's perspective. This particular device did already have someone had gained access to it. Of course, this is all proprietary, so no one's going to tell you anything about it. So I wanted to build up, what would be the steps to actually getting access to it, and how might they have done it. So I don't know exactly what happened, but this is sort of my journey to understand that. I changed a little bit the ECU in use, so I started with mentioning this E99 ECU. I switched to this E41, so this is a slightly older generation one. The main difference is this main chip here is different. So there's going to be some differences about it. The reason I used the E41 was in part at the time it was more available. I knew I'd need to get a few of them. It turns out right now there's this big part shortage if you're not familiar with all the manufacturing issues, so I don't even know if you can get them right now. But at the time this was the case. They were supposed to be a similar generation, so the E41 ECU was supposed to have pretty good security, so people talked about it using secure boot. I don't know exactly if that's true or not. But basically, it was not as tuned as other devices. So older ECUs, tons of tools support them. This one at the time, there was only like one tool that supported it, and it was very unclear, how they did it. So this was also a really interesting target. The other thing I'll point you to is I'm giving you this presentation in 20-30 minutes. I'm going to talk about a lot of different work that happened. Often, you want to know the process, you're curious how you actually might get into that. So I have these 4 YouTube videos that I'm releasing associated with this, and basically they go over, hey, I took the chip off in the end to reverse engineer the pinout, and so you can actually watch me do quasi-live. Some of it's, cut down for time, but for the most part, it's pretty raw. So if you're curious to see, hey, how could you do that? One of the other things I want to point out is that quite a bit of information I've tried to put out there beyond just the classic sort of paper or presentation stuff. So take a look at that if you're interested. So really briefly, these devices, if you haven't looked at the PowerPC, devices before this 5000 series is quite popular in automotive. It was actually jointly developed, so at the time by Motorola and ST Micro. Motorola became Freescale, NXP, due to acquisition, so a few name changes there. Basically, there's a number of these devices that will have kind of the same core and different peripherals from each manufacturer. The part numbers are different. Normally the core, like bootloader and some of that, is very similar between them. So you have to be a bit careful because there's actually a lot of variations of kind of the part generations within NXP and then between NXP and ST, for example. So if you're looking at different devices, just be aware that there is quite a few variations. As an example, I'm looking at two of these from NXP, the MPC 5.5 and MPC 5.6 series, and then comparing it to the MPC 5.7 series. The first two are basically very similar. There's slight differences, and they're very similar in how you program them, which is interesting to us because they have this boot assist module, so that's the first BAM, and they call it in ROM. I don't know if it's flash or not, right? And it basically brings the part up and passes control to the user. The other thing it has is special boot pins that allow us to control some of the boot mode. The other version of it, so this one was used in the E99, if you remember. This one here actually has the same sort of options, but it also has an ability to ignore external pins. So it's a little harder to experiment with. That was the other reason that I started with these devices. And there turned out to be quite a bit of interesting information about, this first device, enough to really dive into it. So that's actually what this talk is all about. So the boot assist module, the BAM, it gives you this really nice flowchart. So you don't have to reverse engineer the code or anything, right? So there's this boot config, and if we get into the right settings, we end up in serial boot in here. And in serial boot, right, they know that people could use this to do things they don't want to have happen. So they basically have this serial protocol. Of importance, you'll notice this password transaction. So basically what you do, you send a password to the device. If the device likes the password, it continues to accept data. You send it data that it downloads, and then it just runs whatever you downloaded. So you've got to make, so this is just like a first stage bootloader. You have to make your own second stage bootloader to actually do anything, right? All it does is run code from RAM for you, if it accepts the password. So what we'll need to do, the kind of point of this talk is mostly about this, is that password, how that comparison works and how you could bypass it. It turns out this is a nice attack because it's pretty low level. So no matter what people do at a higher level, no matter what the ECU manufacturers are doing, this ends up being sort of a problem for them because this gives you access to the core memory itself. How that password is handled depends on some configuration. So I go into more detail on the paper, but really briefly I want to cover this idea that, they call it censorship. So you'll see this name censorship on these devices. With the censorship control, it basically controls if you have a password or not that's used, if that password is what they call public, which is known, or this flash password, which is a password that the customer sets up. Right, so the customer being the ECU manufacturer. So if there's that customer-specific password, we can't easily access the device. And on these devices, on these ECUs, the password is unique per device. So that's very good. Okay, so what's the first thing we're going to do? The first thing I'm actually going to do is use something called power analysis. So power analysis, that's part of what I've talked about a bunch before with Chip Whisperer and in that hardware hacking handbook. Basically, it lets us actually understand the program flow, without having other debug access. So I don't need a debugger or anything like that because that's all going to be closed off in the bootloader. And I'm using just this Chip Whisperer system, and I'll show you a demo of that in a second here, to compare. What I want to compare is like what happens if I send the right versus wrong password, right? So to do this comparison, what we do is I have a custom board, and you can get the design files at that link there. And I've taken the power rail for the device. I've not put what would normally have decoupling capacitors on it. And I use a shunt. And this shunt basically means that there's current's going to flow through this shunt. as the current changes, it changes the voltage, right? And we measure that voltage. It actually turns out that the power being used by a device does vary depending on what it's doing. So if it's just sitting there in a no-op loop doing nothing, it tends to have a different signature than if it's like, using the UART, reading from flash, reading from RAM, all that stuff. And so what I do here is I plot over time an incorrect and a correct password, and then I see what the power usage looks like. So the correct password is in green here, the incorrect one is in red, and this is measured at some point after I send the password to the device, right? So what's interesting is right here, they're perfectly overlapping, and then eventually they kind of diverge, right? Like it splits off. They no longer overlap so perfectly, and that means at some point in time the code path actually changed. So what does that look like? You're probably kind of curious, right? So this is like an example. So normally I'm using this Jupyter notebook thing, and what I have physically, right, is I love doing live demos, by the way, so I didn't want to pre-record it even though I'm recording everything, is I have that target board I showed you a second ago, and so I have this target board here, and then I'm measuring the power with the Chip Whisperer device here, and at the same point we can control, we're going to send different passwords to it. So this code here is just setting up, the password, so it implements that protocol and then checks it gets a response. And I can basically send one of two different passwords. So I'm going to use the public password. This device is just configured with that. And either the first byte is correct, so it's the right password in red, or the first byte is incorrect, so it's the wrong password in blue, right? So if we plot these two, you sort of see, and we could make it, let's make it match the slide, so green and red. I told you I was doing this live, so I didn't even think of that. So now you can see that red, right? Like right here, this is actually where it's going into that infinite loop. There's a bit of a time mismatch. Don't read too much into that. I'll show you in a second why, right? Because what we're seeing here, right, is that the red line, so it's continuing the comparison or something, and then eventually we do see it actually split down into this smaller loop here. And what's this smaller consumption? I actually know that the device just waits for a watchdog reset when the password's wrong. So that's what you're seeing right there. You're seeing the device waiting. If we send the same, so just as a reference, if I send both of these this exact same incorrect, you can see they're a tiny bit, they don't match up perfectly, so there's some jitter here. But you can see that the overall, flow of these look very similar. And we can try like a different but yet still incorrect password and see again a little bit of jitter there. So that's what I was saying when, don't read too much into the fact there's a time difference. There may be a timing attack available that would let you brute force it. The issue is that it's a 64-bit password. You have a limited baud rate, so it's 24 kilobits. This serial console is running at. Basically, it's fixed. You have a 64-bit, and it's not just ASCII. You can actually send any password you want almost. So you have quite a big search space. So if you were to brute force this is not super trivial to brute force. If there's a per byte timing attack, you may actually have something more useful there. So I didn't explore that too much because what I was really interested in is, can I target that point in time? So if I look at that point in time, can I say, let's use electromagnetic fault injection to make the code path diverge. So with electromagnetic fault injection, what we have is a small coil. So there's a coil that we put a pulse into. You put the pulse into that coil, and it can actually disrupt the execution of code on the device. So as a little demo here, so I previously did a talk on a Trezor wallet where I was using electromagnetic fault injection for that. At the time, so I disclosed it to Trezor so they could patch the problem. And they gave me a Bitcoin, which I put on one of their wallets as a reward. At the time, that was like 10K. And so I did a live demo using it. So this one here, I don't actually have the Bitcoin on it anymore. But what we can do is I can show you, just as a kind of quick rehash of what that looks like. So I'm just going to move that other stuff out of the way a little bit. And we have our, right, so we have your Trezor. Zoom in on that. So it's just, I haven't really set it up yet. So what we're going to do now is I'm going to use a fault injection tool. So this thing here is just basically charging a voltage that it's putting into this tip. And so when it goes into the tip, we'll put this over the device and you'll see sort of incorrect, you know, so it can corrupt memory, it can do all sorts of stuff. So it's going to be a very straightforward demo. And I'm just going to kind of hold it over this when I hit it, right? And what you'll see is that you might see various, you'll see, normally see the device like reboot and stuff like that. But you may also see, right, so like there you have this stack smashing detected. So I've actually tripped some of the protection in it. So you'll see all sorts of faults inserted. And so some of this can be like hard fault, you know, some of this can be memory corruption, code flow corruption. There's all sorts of effects you can have. So it's not incredibly scientific a lot of the time, but it turns out that it's highly effective. And I'll show you that being highly effective on this type of device too. So basically what I did is I used that setup I just showed you. So I used the chip sharder tool, put it over top of a chip, sent the password. At the time I got the password and I kind of had that timing from the power analysis, insert a fault. And what you want to see is, did it accept, so if I take the wrong code path, it actually accepts that password. So even though the password was incorrect, it thinks it's correct, and we're happy, right? That's exactly what we want to do. So I compared this, so I used that board that I was showing you a moment ago, right, that where I was doing power analysis on. This is my own dev board designed for this work. But the sort of interesting thing is not just, you know, can we do it at all? Can we do it on like a off-the-shelf dev board? So I also compared this on the dev board provided by NXP. This is interesting because this would mean this is like the type of board that a developer would use. We also had the actual ECU. So this is the ECU pull, you know, from a car, so you can see the microcontrollers on there. And I kind of have some test points attached to it, right? Various spots. So I basically have like the serial console goes to a chip, so I click off that. There's some pads with the reset pins and stuff like that. And finally, I compare the success rate on a similar device, the MPC 5566. So it's similar, not the exact same device. Because the other question is, I mentioned earlier, right, these have a lot of variations, you know, even within the same family. So how well does this attack translate between different devices? Because I don't just want to show you, hey, it's cool, I can attack one device, great. But what does that tell you to someone designing it, someone evaluating a system? So I tried to evaluate this across many devices to give you a better feel for how repeatable these results were. And we could basically break down the results into a few different classes. So I mentioned that bootloader protocol before, so we can detect stuff because of that protocol really simply, like the device reset. So if I see it is in looking for the initial synchronization, I know it reset. Normal means it did not accept the wrong password. We have some protocol and other errors. So protocol errors mean something got corrupted on the transfer, which we don't want because then, you know, we're not able to download it. The other one that has some overlap is what I call run fail, where it looks like it works, but it didn't work in the end, right? So like the code didn't run, or the code ran, but it wasn't able to read the internal flash memory, which is what we really want. So these could be corruption. These could be like the device wasn't wasn't unlocked like I planned it. So finally, we get success where it accepts the password, the code downloads, the code runs, and it has access to the internal flash memory. So in the full paper, which I'll link, I also go through, you know, it's easy to get false positives where the code does download, but it doesn't actually execute. So you have to be a bit careful to make sure you are getting a success like you think. So here's the results across, I mentioned those 4 devices. So the 308 is that custom dev kit. The 5676 is that off-the-shelf dev kit. And all of these, and there's some variations between what password I tried to send to see if that mattered. You're like 1% to 2% success rate, which maybe doesn't sound like a lot, but if you think I can send 100 tries, you know, if I send 1, it takes about a second or 2 seconds. You can basically get a success pretty quickly, right? So these are pretty reasonable success rates. The other one is there's a series of information on the E41. So this is where I had the real ECU. And so the difference here is I actually had an interesting result where I got 0 successes at first with the same coil that was used on the dev kit. So when you're doing EMFI, there's a lot of different variables. One of them, if I go back to, what is EMFI, there's actually the direction of this coil winding. So this impacts the polarity of the pulse that gets inserted into the device. So it turned out that mattered more than I thought, because what I was seeing is that on the dev kits, it worked just fine. On the real board, it didn't work, and it came down to actually needed the opposite polarity. So another point, sort of take home here, is to show that it is important to evaluate these devices across kind of a wide variety of settings. Finally, I used the 5566 device. Again, another sort of interesting result here was that it was highly successful for one of the password configurations. So I tried sending different incorrect passwords. So it was highly successful for one of them, but not successful for the other. And that was not the case on, the ECU. For the ECU, it was actually pretty similar between the two of them, right? So for the ECU, I sent this 1122 private password, and that would work. For the ECU, I could also send the public password incorrectly. That would work. For this 5566, only sending the public password when it shouldn't accept it seemed to work. So this is, one of the really interesting things with fault injection is it's not perhaps as scientific. So it's really important to sort of figure out what your search space is and make sure you're trying to cover that. Because if I had only tried one coil winding on the E41 ECU and hadn't tried the dev kits, I might have thought, hey, this is actually not going to work at all. But it turns out it works really well. So that's sort of one of the other take-homes here. The other thing I wanted to experiment with was, well, okay, this is great. I'm using that Jupyter notebook like I showed you. What's the real threat here? The real threat is people like car tuners, garages that are using this. They probably aren't going to want a Jupyter-powered Python script. So I wanted to show this with a more sort of standalone setup. And to do this, I also wanted to demonstrate it's not incredibly complex. The most expensive part, of course, is the EMFI tool. There are open source and other EMFI tools like BadFet have been presented, and there's a few different ones now. So that's really, by far the most expensive part, not the controller. But the controller doesn't have to be very complicated. So I use an Arduino. It understands that protocol, so that bootloader protocol I showed you. It can talk to the ECU, send a password, generate a pulse to trigger the EMFI. The timing wasn't super specific, so it would actually work really well. It can give you some feedback, and when it successfully executes, it reads the password back as it's printed out. I took that a little step further, so I also made this this setup here, and so you basically have so this was also some in-progress work on like this chip shover, this XY table. So there's a controller. You can see it's like half open because I'm still working on it there. But basically you have like a similar idea, but even slightly more advanced. So if we switch back to this other camera here, I can show you here. I left it connected. I'm not going to run it all because it takes a little bit to run this thing. But I can show you that you basically have like a setup where we have a ECU that can be kind of mounted, right? I have an Arduino controlling it, so we can go ahead and plug that guy in. So we'll power up, right? And so it'll talk to the ECU, try to detect if it's running or not. On the flip side, so in this case, what I was doing actually is I found the positioning wasn't super specific, but you can set this up, of course, to like scan across the surface. So there's obviously lots more we can do here. That's kind of one of the other in progress. So yeah, that's like a really fast overview of how this attack worked, how the fault injection on this device worked, how the bootloader works, and how I actually discovered some of this. So if you're curious, I've got a lot of resources here for you. So the video links that I showed earlier go over some of my process. There's a link to my blog post where I talk about this, and I have a longer paper explaining some of the timings and other stuff as well. So I've linked that below. General related material, so if you're kind of curious, about fault injection, power analysis, the Chip Whisperer repo has several tutorials that go over this topic. The upcoming book, of course, I'm going to plug that as much as I can now. And finally, there's this other app note I wrote here that might be sort of interesting. This also talks a bit about safety testing, but it's looking at EMFI and actually how it relates to fault injection that is actually commonly used for safety testing in automotive. So if you're coming from an automotive environment, you might actually already be familiar with some of the terms used. It's just been wrapped a different way. So this white paper goes over some of those combinations. But thanks so much. Hopefully we have some time now for questions, and you can reach out to me also on Twitter afterwards if you have other questions that I didn't cover here.